Is it on? Yeah.
Mine's not. Is mine on? Mine's on, yeah. Good. Hello, everyone. Welcome back from lunch. Thanks for coming along to our talk. This is Martin.
Hello.
And I'm Doug, and we work for Underscore. Underscore is a software consultancy, largely based in the UK, but with various people scattered around the world. We do project work for clients, mostly in Scala, some big data, that kind of thing. Also a lot of Scala training. And some of our people have written a variety of books, including this one, Scala with Cats. We have a few printed copies to give away at the end, so come up and grab one. Anyone who asks a particularly good question will get one as well. It's still free, but at least you'll know you won yours. Okay. So today we want to talk about Droidspeak. This is the result of some work we did on a client project recently. And what we're going to talk about is the problem that the client came to us with. First, we'll take a look at the technical solution we came up with to address that, and why that maybe wasn't the best we could do on the project. And then we're going to introduce what's called a domain-specific language that helped us really reduce the gap between the conversations we were having with the business and the actual code that we were writing. And we're going to explain, doing that, a couple of features of Scala that we use in order to make that possible.
Cool. So the client approached us with a problem. The problem was they were manually collecting data from their customers and then manually making decisions based on that data. This had a couple of issues. So first issue was it's quite time-consuming to do this manually. And second issue is because it's humans involved in the decision-making process, it's inevitable there are going to be a couple of mistakes along the way. So the client asked us to automate the second part of the process, which was making the decisions from manually collected data. The client codenamed this project R2, so there's going to be a few R2-D2 and Star Wars references littered around here. Does anyone know what day it is today? Yes, exactly. We managed to convince flatMap to hold the conference on May the 4th, just to align with our talk.
So the client gave us a bunch of specifications which were in the form of decision trees. What's a decision tree? Well, here's a really simple one that I use to decide if I should have more coffee, because I love coffee, and in Oslo you've got some great coffee shops. So left to my own devices, I'm going to end up completely wired. So it's very simple. Is it before 3 p.m.? Yes. Have I had less than 3 cups of coffee today? Yes. Have another coffee. But if I've had more than 3 cups of coffee, or if it's after 3 p.m., then I'm just going to chill out with some green tea. Okay, so that's really simple tree. We're going to use that as an example as we go through explaining what we built. Obviously, the trees that the client gave us were somewhat more complex than that, so we're also going to bear that in mind as we go along.
Yeah, but if you look at this as a specification, it's actually pretty awesome. It's really specific. There's no ambiguity whatsoever. And it really kind of opens up the specification to discussion across the team, cross-functional team, because everybody can reason about decision trees and understand what's happening in the spec. The only issue with it is it's not code. You can't go on the Amazon AWS console and spin up an EC2 instance from a diagram. That's not a thing. We've got to encode this in software in some way. So what we're going to do is talk you through a couple of implementations of this and assess it on 3 criteria.
So the first criteria is composability. This is a good property of any piece of software. We wanted to be able to take large things, break them down into smaller pieces, reassemble them, and hopefully reuse some of those smaller pieces where it's appropriate. Second property we're going to look at is completeness. What we want is that any input we give our program, we want it to come back with some sensible result. We either want, in this case, to reach a decision or come up with some sensible error message as to why we couldn't. What we don't want is to feed some data in and for the whole thing to throw wobbly and decide it can't make it do anything with it and throw an exception, for example. Now, we're using Scala, so we want to help have the compiler help us to ensure that we've achieved that completeness property wherever we possibly can. The third criteria is readability. This isn't just readability as Scala code, but also that we should try and reduce the amount of effort it takes to translate what we're talking to the business about into the code that we're writing, and vice versa. We also knew that we needed to hand this code over to a client's development team at the end of the project, and we wanted to make sure it was as maintainable as possible for them. So this is quite a subjective criteria, but we're hopefully going to know when we don't have it in our code.
Cool. So this is our kind of checklist for what we're going to mark our implementation against. So there's a 3 success criteria that Doug just explained, and we're going to introduce 2 techniques. And the whole goal of this is to reduce the gap between the specification of software and how the business talk about problems, essentially. Before we get into tree implementations, however, we're going to need to introduce a couple of tools first. The first tool is we need some data, so we're going to need some data access. All the data in this project was locked away in a proprietary system, and the API to it was essentially a map of string to string, so stringly typed data, essentially. We introduced an abstraction called a field, and a field captured 2 things. The first thing the field captured was a parameterized type T, which was the Scala type that's higher level than a string that we want to work with. And the second thing it captured was the name of the field, so the key of the map, essentially. From this, we can define a few fields. So here we've got age, which is an int. We've got name, which is a string. And we've got has the force, which is a Boolean. When it comes to actually accessing the data, we obtain a data source through some mechanism. We can then use the get method of a field to apply a data source and retrieve the result of the Scala value that we want to work with. So notice I said the result of. This might fail, so there's going to be some validation along the way. It might fail if the key isn't present in the data source, or it might fail if the string value of it can't be marshaled in a meaningful way into the Scala type we want to work with.
Okay, great. So now we have a way of accessing data for our system. We need a way of interrogating it with simple questions. And in order to do that, we're going to build what's known as an algebraic data type, or an ADT. So what's an ADT? At a very high level, conceptually, it's just a way of modeling concepts in the system as data. As I said, that's pretty abstract. So let's take a concrete example. Let's pick a couple of concepts, or a concept to model, which is a drink. And the drinks we're going to consider are green tea and coffee that come from our decision tree. So if we look at it, coffee is a drink. We can put milk in coffee, and you can maybe put some sugar in. So we want to capture that. Green tea is also a drink. We can put sugar in it, but it's travesty to put milk in green tea, so we're not going to allow you to do that. This is what an implementation could look like in Scala. We have a trait, which is drink. That captures our concept. And we have 2 shapes of how drinks are going to look in our system. Coffee and green tea that take those parameters that we just mentioned. Important thing here is that sealed keyword on the trait. That tells the compiler that these 2 shapes of drinks are the only ones that can exist within the framework of this system. And that's really going to help with the completeness property that we're looking for, because anytime we need to deal with a drink, the compiler can tell us if we've dealt with all the cases that can exist. And we can actually get the compilation to fail if we haven't.
Cool. So going back to our tree, the smallest unit of logic in the tree is a predicate, which is basically a question that can be applied to some data. So in this example, we've got number of coffees I've had today is less than 3. That's an example of a predicate. Let's try and model this as an ADT. So the first thing we need is the data field that we're going to interrogate. This is going to be number of coffees today, which is an int. We then go through this mechanical process to build up the ADT. First of all, we introduce a sealed trait called predicate, and we're going to introduce 1 shape of it. The shape is going to be called less than, and it's going to capture 2 things. First of all, it would be the field that we're going to obtain some data from, and that's going to be a generalized field on an unconstrained type T. And the second thing will be a constant of the same type T that we're going to compare against. Now, because T is completely unconstrained, we don't have a meaningful way of being able to tell whether one's less than or greater than the other currently. So we're also going to capture a third thing, which is an ordering of the same type T, and this will let us do that comparison. When it comes to constructing an instance of a predicate, it's very simple. It looks like this. We instantiate a less than on our number of coffees today field with a constant of the same type of the field, which is an int number 3, and an ordering of int, which also aligns with the field type. But notice here, this is purely an expression. It has no method. It has no opinion about how it should be interpreted. That's a completely separate concern. For that, we build an interpreter. Here's an example of one, and it's a really mechanical process to build. So all we're going to do here is we're going to do a pattern match in our ADT instance of predicate. The Scala compiler is going to force us to consider each shape of predicate. We've only got one, which is less than. And we're going to extract out the field, the constant, and the ordering from this less than. We can then use the field to get a value from the data source. We can map over the happy path to retrieve the T back and use the ordering to compare it against our constant. And if we run it at the bottom here, we can get back a validated Boolean, which indicates whether our predicate is true or not. That's not the only possible shape of interpreter. We can build a much simpler one by just matching and constructing a string representation of the predicate. This is going to be really useful later because we're going to generate some documentation from these trees. Cool. So if we go back to our checklist and where we're at currently, so our goal was to reduce the gap between software specification and the business. We've talked about ADTs now, and we've shown that they give you completeness. So now let's see what other success criteria they can give us.
Okay. So now we have the tools to talk about tree implementations. So what we're going to do next is we're going to build an ADT for complete binary decision trees. And we're going to build those on top of the predicate interpretation that we've just seen. So again, here is the shape of the tree. We have leaves that capture a decision or an outcome, and we have branches that capture a predicate, and two subtrees, one to take if the predicate's true, and the other to take if the predicate's false. So this is what the Scala code looks like. We have our concept of a tree. It's a sealed trait, and we have two shapes of that, the leaf and the branch. And one interesting thing to note here is that the yes and no in the branch themselves point back to tree. So this is what's known as a recursive data type. It allows us to build arbitrarily nested trees. So one thing here, though, is that this tree only handles drinks at the moment. And it would be really annoying if we had to build this kind of tree structure for every type of decision we want to make in our system. So we can do a bit better. We can pull that out as a type parameter on the tree and on the case classes. And now we can build trees for any type of outcome that we like. So how do we use a tree to make a decision? So let's ponder this decide function. Martin's already talked about interpreters, and this will be an interpreter for our trees. So first, let's assume that we have a function that can check a predicate and return a Boolean. We know that tree is an ADT, so according to the same pattern, we match the tree variable, and now we need to deal with the two cases of leaf and branch. First one's easy. If we've reached a leaf, we simply unwrap its outcome and return it. We've reached a decision. And if it's a branch, what we'll do is we'll test the predicate, and depending on whether the value of it's true or false, we will decide whether to follow the yes or no path. And branch handling is recursive, so it's going to call back to the decide function, and it's going to keep going until it finally reaches a leaf. If you recall, our actual predicates evaluate to this result of Boolean, that something can go wrong in terms of fetching the field, for example. Luckily, we only need a little bit more code to handle this. We can just thread the data source as a parameter through our calls, and we change the return type to wrap things in a result. And so now we've got a practical function that can interpret our tree with some error checking along the way. So let's look at how we would code our simple tree using this ADT. Okay, from a technical point of view, it's great. what we have is Scala code that directly represents the structure of the tree. And that's easy when we're so we can look at the diagram and we can look at the code, and there's kind of a one-to-one mapping. Trouble is, it really doesn't scale up terribly well. We still have a direct mapping here, but we have a big chunk of code. It's really hard to see which part of the tree maps to which part of this deeply nested chunk of code. And if we want to change the requirement, then it can be kind of hard to find where to go to in that code. Of course, this is Scala. We can pull some of this stuff out and get composability by using intermediate vowels. So from a readability point of view, this looks a little bit better. But it's still not great. Now we've lost that one-to-one mapping. And it's much harder to see the structure of the tree in the code. So we're getting the trade-off here, it seems, between composition and comprehension, or readability. So let's look at what we can do to try and address that.
Cool. So if we go back to our goal, which was to reduce the gap between software specification and the business, we've got ADTs, and we've shown that they give us some way of composing and definitely give us completeness checking. But we're going to say that they're not going to give us readability. And the reason for that is it's a cross-functional team, and not every team member thinks in terms of leaves and branches. It's a completely different way we talk when discussing requirements with the rest of the team. So to kind of gain this third criteria, we're going to introduce a DSL for decision trees. And the process we took to basically end up at this DSL was to stop thinking about the tree in terms of as a whole or a direct representation, and instead think about it in terms of paths. Here's an example of a path. So this is saying, if it's before 3 p.m. and I've had less than 3 coffees today, get a coffee. And there's 2 more such paths through our tree. So then we thought, okay, let's try to represent a tree as a collection of these paths, or a list. We then did something a little bit interesting, but hopefully you'll see why in a second. We kind of turned this tree upside down, and we said, well, actually, it's a lot more natural to think about a path in terms of its outcome, and then the reasons why you ended up there. That was much closer to the way requirements were given to us and problems specified to us. So we then encoded this in Scala and ended up with a syntax kind of similar to this. So now what we're going to do is kind of break this down, show you the mechanics of it, and show you some of the properties that we can achieve by using this syntax.
Okay. So each of our paths looks reasonably simple and quite natural. And a path is made up really of 2 parts. So let's build a case class to capture those 2 parts. First, we will grab the outcome and pick that in there. And also what we need is a list of predicates that can lead to that outcome if they all evaluate to true. So what we want to do is make this nice line at the top, which is our DSL, turn into this line at the bottom. Because at the moment, that doesn't compile in Scala. Coffee doesn't have a when method on it. Cups today doesn't have a less than method on it. So we're going to need to do some work in Scala to make the compiler able to handle that. And we kind of need to address two things here. The first is those predicates. So when we say cups today less than 3, the compiler needs to turn that into an instance of our less than predicate, capturing the two values there. And similarly, those whens have to turn into predicate tests that form a path to that outcome. Okay, so what we want to do is we want to take this nice, compact, simple, human-readable form and turn it into something that's explicit and type-checked for the compiler.
Cool. So just really a few words about the mechanics of what's going on under the hood here. So this is what we want to do. We want to be able to build predicates using our syntax. In Scala, this less than symbol is actually a method call. So it looks something closer to this. The only issue is number of coffees today doesn't have a less than symbol method. So we introduce an extension method. And this isn't purely a Scala concept. It's similar patterns in many languages. The way you do it in Scala is by introducing an implicit class that is bound to a value of a certain type. So in this case, we're going to introduce an ordered field implicit class, which targets fields of any type. And this will essentially adorn it with this less than symbol method, which takes in as a parameter a constant of the same type that the field holds data for. From there, we can then construct a value in our ADT instance and return it as a predicate. So we're returning a less than with the field that we're targeting and the constant that we've captured. If you remember back from our less than ADT, there was a third thing, the ordering there. So we're also going to specify that there's another implicit requirement to be able to use this method, and that is there has to be an ordering available for whatever T you're capturing. So at the end of the day, we end up writing code like at the top, and the compiler is going to rewrite it, improve certain properties, and construct code closer to what's at the bottom of the slide there.
Okay, great. So if we go back to our criteria, we have, I think, definitely improved the readability of our code by rethinking things in terms of paths and coming up with this syntax to let us express paths more clearly. And that's helped us align the code we're writing much more closely to the kinds of conversations we're having with the business. Let's take a closer look at composability and why it might be useful when building these trees. So as we said, composability is being able to take small pieces of given type and build them up into larger pieces. And that lets us break off the big stuff into smaller things and reuse smaller pieces. If you look at this tree, then we can see that these three subtrees are actually identical. The one at the bottom might not immediately stand out, but if you look at the predicates and outcomes, it's actually the same subtree. Let's take a slightly smaller example. Let's go back to our original example and extend it a bit, and we're going to add in an extra test. Is it after before 3 p.m.? No. Is it after 5 p.m.? Forget coffee and tea. We're going to go have a beer. Now, that means we now have these two subtrees that are identical, and can we break those off and reuse them in some way? If we write out the paths in our path lists, as we've done before, we now see we have 5 paths instead of 3. But these 2 bits are identical. And it would be great if we could pull those out. So let's do what you do in Scala. You pull them out to an intermediate val. Brilliant. So now we've got coffee or tea, which is a list of these 2 subpaths, and our main path list, which builds up out of those. But hang on. The types don't quite work out yet. Coffee or tea, when we extend it, coffee or tea is a list of paths itself, but we're trying to put it into another list of paths. So that doesn't work, because we're going to end up with kind of a list of paths. We need some way to let us take that list of paths and turn it into something path-like, but representing multiple paths under the hood. So let's revisit our path class and have a look at what we could do there. At the moment, it looks like this. It's a simple case class, just has one shape, and it doesn't quite work for everything we need. So let's turn it into an ADT. Let's make path a trait representing the concept of a path, and now we have 2 shapes. Our simple path is what we had before, and we've got this new thing called a multipath that just wraps a list of other paths. And we'll see in a minute how we're going to use that. But now we can make this code make sense. Coffee or tea is a multipath, and we can extend it with further predicates, but it will still be a path. So our main path list, quite nicely, now type checks. It's a list of paths. Okay. So the next question is, how do we make that when syntax work? Again, beer doesn't have a when method on it. Multipath doesn't have a when method on it. Let's walk through how we're going to do this. Now, we've already seen the way to add syntax is through extension methods. We're using when in 3 different ways. So let's have a look at those. First, we're using it to initiate a path from a given outcome. So we could introduce this syntax, this implicit class that targets an arbitrary type of t, and will provide a when method that takes a predicate, and it will simply build a simple path that captures the outcome value and the predicate. Second, we need a way to create a multipath from a list of paths. So we have this implicit class that targets a list of other paths and will build it has a when function that will build a multipath out of that. It simply wraps the paths into a multipath. And lastly, we need a way to extend an existing path with a new predicate to form a new path. And this implementation follows a familiar pattern for an ADT. We pattern match the path variable, and we deal with the two cases of simple path and multipath. For a simple path, we just add the new predicate to the list that it contains. And for a multipath, we're just going to map over the paths that it contains and extend each of those in turn. So that's great. Now we've got a way to analyze the paths in our tree, write them down in a much more readable and composable way. It's all type safe. It's looking good, isn't it?
Yeah. Yeah, if we look at our goal, which was to reduce the gap between software specification and the business, we've got two techniques, and they've got us quite far. We can compose with them, and it's readable, it's maintainable, it's expressed in the same way that we're talking as a team. The only problem is we're not sure if we've got completeness now. And what I mean by that is if we take a look at this code snippet, it's completely valid. There's absolutely no tricks here. It's a list of two paths, and it uses our DSL syntax to specify the paths. The only problem is this is the tree it forms visually. Basically, if it's after 3 p.m., I have absolutely no clue what drink to get because there isn't a path for that. So we need some guarantees here that we're not just basically feeding in incomplete lists of paths to our system. How did we get here? So we started off with a specification that had complete binary decision trees. We encoded it as a list of paths, which was a more maintainable solution. And now we're going to introduce a compiler which takes in this list of paths and builds out instances of our complete binary tree ADT from our very first section of the talk from there. The signature of our compiler looks kind of like this. So it's a method, it takes in a list of path, and it returns a tree. But it's a result of a tree, so it's going to be validated, and we're going to fail with a meaningful error if it violates one of the completeness properties of binary decision trees. So this is kind of how the algorithm looks visually. So we feed in this path list to our tree compiler, and the very first thing we do is pick a pivot value, which is a predicate, and it's the outermost predicate on the very first path in the path list. We then do something that might sound a bit odd, but we compute the inverse of the predicate. So if our predicate was, is it before 3 p.m., we're going to compute, is it 3 p.m. or after? We then subdivide our input list into two sublists of paths. So first of all, it's the list of yes paths, all of which have an outermost predicate that matches our pivot. And second of all, we compute the list of no paths, all of which have an outermost predicate that matches the inverse of our pivot. We then eliminate the outermost predicate on each of our paths, and we're left with a smaller problem now. We've got a set of yes paths and a set of no paths. From here, we can build out a branch, and the branch is going to be on the pivot predicate. The yes tree that it pulls in is going to be the recursive compilation of the yes paths. The no tree that it pulls into this branch is going to be a recursive compilation of the no paths. Our kind of termination condition of this recursion is if we ever get fed in a path list of exactly one path that has no predicates remaining, we're going to form a leaf. And this algorithm can blow up in various ways and detect what various properties are being violated. So one thing that could happen is we could be fed in a list of two paths with no remaining predicates. Now, we've got no predicate to be able to decide which leaf we should build, so that's going to be a failure termination condition, and we're going to refuse to build this tree. The other thing that could happen is when we're dividing our path list up into two, into the yes paths and the no paths, we might only find yes paths. That means that we're missing some logic from our tree. And again, we can feed that back through validation and basically just refuse to operate as a service because our code is incomplete. So the mechanism I kind of introduced there, it sounded small, but it's really, really important to the algorithm, is we need to be able to invert a predicate. What does that mean? It means if we have a pivot of now less than 3 p.m., we need to be able to compute its inverse of now greater than or equal to 3 p.m. Now, if we look back at our ADT of predicates, we just have one shape currently, which is less than. Now, the mechanical thing to do in this scenario is to introduce another shape, greater than or equal to, that basically captures the same stuff and then constructs that through some syntax, which is the greater than followed by the equals symbol. From there, we can basically build out this inversion interpreter in which we pattern match on each predicate, and we just return the opposite shape in each case. But this had a couple of issues, because every time we introduce one of these operators for predicates, we have to grow this inversion interpreter, and it could be quite buggy, right? We might return the wrong inverse in a case. So what we actually did was a bit of an optimization, and we generalized this by introducing a not predicate, which recursively takes in another predicate that it's going to invert. Our syntax for greater than or equal to didn't change whatsoever. It just returns a not of a less than of a field, constant, and ordering. And the big win with this was our inversion interpreter was dead simple. All we have to do is match on the predicate, say if it's wrapped in a not, just unwrap it from the not, and if it's not wrapped in a not, wrap it in a not. And there we go. That's full circle. We're never going to have to grow that interpreter with the language. So essentially what we've done is we've taken our spec, we've encoded it in a different way, and as we've encoded it completely as data, we're able to go back and prove certain properties and traverse it as a binary tree. So the next kind of logical question is, when should we run this tree compiler? Well, we could have done something like quite intricate, like a macro, or instead use shapeless or something like that. We chose a much more pragmatic approach, which was a test that will fail the CI build if we specify an incomplete path list. It's just something like that, essentially. The other thing we kind of do, which is, again, kind of a pragmatic belt and braces thing, was we'll disable a service if its path list was incomplete. So then we would be able to see in the production logs that yeah, we basically missed a whole bunch of paths. So if we go back to our very first goal, which was to reduce the gap between software specification and the business, we've actually nailed it with these two simple techniques. That's all we did. We just used ADTs to represent our logic and our data, and we used a DSL to give a syntax that was closer to the way we're talking about the problem with the team. And we've ticked off all our success criteria.
Okay, great. So now we have this nice function that will take a list of paths and build trees from them, and that means that we can go back and we can use the decide interpreter that we wrote earlier on those trees. So we've come full circle here. But because our trees are just DSLs, ADTs, we can do other interesting things with them. And a couple of things that we did on this project. The first was we made an interpreter that would actually generate graph viz diagrams from these trees. So we could recreate diagrams from the paths that we wrote down. And that served us both as a really good way to sort of visually compare with what we were given and make sure that they looked the same. And also it worked as really good documentation when we handed the project over, because even if the maintainers didn't have access to the original input requirements, they could still create these nice tree diagrams to work with and look around. Another interesting thing we did was we built a modified decision interpreter that would actually record the path that was taken to the outcome. And this let us generate human-readable explanations of how we reach decisions. And we could send those descriptions back to the user along with the results. So this helped greatly reduce confusion in situations where maybe the user saw decisions that they weren't expecting. Rather than having to come to us and ask, well, why did this happen? They could actually see immediate feedback and an explanation and decide if that was the right thing to have done. Great. So in summary, what we've done is we started out by taking our requirements and building a sensible technical data model out of that. But we found that there was this degree of translation that we were having to do in our heads as we talked to the business and worked with the code. We reimagined trees as lists of paths because that matched the kind of conversations that we were having with business people. And we came up with this DSL to represent those paths as valid Scala code. And in order to do that, we used just two features of Scala, really. We used algebraic data types, and we used extension methods. So we didn't have to go in too deep, use anything particularly fancy to make this happen. And then finally, to close the loop, we wrote something that proved that our lists of paths formed valid trees. So really, what we'd like you to take away from this talk is this idea that you can look for ways that maybe the code that you're writing isn't matching the way that you're communicating with your client, and that you can perhaps think of a better way of expressing that in Scala and see if you can apply some of these techniques to make that syntax work for you. Thank you very much. That's all we've got for you today. Are there any questions? Yes?
Does the British immigrant or British authorities use a system like this for immigrant applications?
I would not like to comment, but I'm not sure they use any kind of system. They certainly don't use our implementation.
Yeah. I think I heard quite a few years ago, maybe 10 years ago, that the British authorities considered a knowledge system for such purposes.
Right.
Yeah.
I mean, obviously, the decision trees can apply in lots and lots of different places. So. It's a question of whether you can really boil down the questions you're asking to simple yes or no answers in order to do something like this. Yeah.
What was the customer reaction to the DSL? They like it? Using it?
No, they're definitely using it. They seem to be very happy. We, yeah, I mean, one of the interesting things was that we started the project by building these manual trees and so forth. And it was during the course of the project that we came up with this idea. And we had to work to persuade them that actually by going back and really looking at this as paths and DSLs, that we could, first of all, make the code clearer, but also implement new trees faster. And something of a big ask, because they were already putting the first couple of trees in production and getting value from them. But yeah, we did, and it did make the subsequent work a lot faster. So I think they were happy. Were they happy? They're certainly using the system.
Any more questions? Yep, the back. Oh, okay. Right. Okay, so the question was, how did we get these decision trees, was it? No.
Today,
Yeah.
if the people that use the system,
Yeah.
they want to check what the decision tree is now, where do they look?
Okay, right. So the question was, how do we get these decision tree diagrams out from our implemented software? And the answer is we had another main method, so they just run an SBT task. It spits out a few PDFs of each tree we've implemented, essentially.
Do you deliver PDFs?
Yeah, so there's an SBT, yeah. An SBT task that can generate the PDFs, yeah.
So do they themselves get generated, or does a technical person give it to them? Or are the programmers the ones that sign off?
All right, so they can generate it themselves using the SBT task. It'll be the programmers that do that, I think, but there's nothing stopping them extending it to run on CI build or something like that, definitely. Yeah. Question in front.
We didn't look at any automated way of reducing those trees. Part of the reason is that, in a sense, the execution of the trees has side effects in that we're pulling fields out, and if you try and reorder decisions, then you can end up having paths that you don't necessarily need to go down that are trying to get data, and the aim was to have them be able to fill in their forms with just the information they needed to get their decision. So reordering trees is problematic because of the side effects, but also the diagrams they provided us were conversations, so we would sometimes see things in those diagrams that we would go back and question about and so forth, and the business analysts would change them slightly and so forth. So it was also a process of them learning about things, but they really did kind of represent the way that their manual workers were making those decisions. So we wanted to retain as much of that knowledge as possible and not try and circumvent that. It was there's not a high performance system that needed that level of optimization, really, so it was not worth going down that route.
There are situations with your customer where the decision could not be boiled down to yes or no. Maybe there are situations where the answers are a bit more complex than just yes or no. But maybe you can break down the more complex answers to several yes or no answers. That's the question.
Right. So the question was, does an outcome have to be yes or no? In this case, no, it doesn't. We parameterized it on just a generalized type. So it could be yes, no, maybe. It could be whatever criteria is appropriate in a domain, essentially. It's completely up to them.
So the yes, no you presented here is a kind of simplification.
So yes, no is at the predicate level. A predicate is always yes or no. But we can take a bunch of predicates to reach outcomes that might be yes, no, maybe, if that makes sense.
Thank you very much. Your time is up.